Now, suppose that I've got a more complicated system. I'm going to follow this using an example instead of talking about it more generally. And hopefully you can see in the steps that I take during the example, useful steps to follow. I need to switch off. Now, let's suppose I've got C1, C2, C3, C4, and C5. And let's suppose that I know that delta V between point A and point B is 24 volts. Now, let's say that I've got C1 is equal to 3 microfarads, C2 is equal to 6 microfarads, C3 is equal to 4 microfarads, C4 is equal to 12 microfarads, and C5 is equal to 10 microfarads. What I want to do is I want to find the charge and the change in electric potential over each capacitor. Well, that looks like a huge order, but it's possible to do that. Let me just check and see exactly how much room I have to work with on the board. I might have to go through a couple of steps and record a couple of things. Get that over there, make sure everything is included. Okay, now, in these systems, the equations themselves are going to be fairly short. I think of this as like an accordion. We have to be able to use them in the right order. So we're going to crunch everything together into one equivalent capacitor and then pull everything back out. So, for example, here, the equivalent capacitance of C1 and C2 is equal to, well, I've got two capacitors in series. So I know that 1 over the equivalent capacitance of 1 and 2 together is equal to 1 over C1 plus 1 over C2 is equal to 1 over 3 microfarads plus 1 over 6 microfarads, which is equal to 1 over 3 microfarads is the same thing as 2 over 6 microfarads. Sorry, I only have this much room to work. And I'm kind of hoping on the fact that if I go too quickly, you can pause and look at some of the math steps. So therefore, 1 over the equivalent capacitance thing 1 and thing 2 is equal to 3 over 6 microfarads. So the equivalent capacitance of C1 and C2 together is 2 microfarads. Now, C3 and C4 are in parallel. In those cases, for parallel capacitors, the capacitances simply add. So, C3, 4, I hope I don't need to go through the details of addition. And those two together are 4 microfarads plus 12 microfarads, or 16 microfarads. Notice that the correct answer this is the correct number of significant figures because of the rules for tracking significant figures while adding things together. Go back if I have films on this. If you don't see how that follows here to here. Now, I now have the equivalent capacitance thing 1 and thing 2, or at this point I have the equivalent capacitance of 1 and 2 parallel to the equivalent capacitance of 3 and 4. In series with capacitor 5. So, 1, 2, and 3, 4 are parallel to each other. So the equivalent capacitance of 1, 2, 3, 4 is equal to 2 microfarads plus 16 microfarads, or 18 microfarads, all the way back around, 1 over the equivalent capacitance, because now I have, 1 over C1, 2, 3, 4 in series with C5. That's equal to 1 over 18 microfarads plus 1 over 10 microfarads. So the equivalent capacitance of the whole shebang is equal to 6.429, keeping an extra significant figure here because I'm in the middle of a problem, microfarads. Okay, so the equivalent capacitance of the whole thing is 6.429 microfarads. Now, how does that help us? Okay, if I'm looking at the equivalence of the whole thing, then Q, the charge stored on that equivalent capacitor, would be equal to the equivalent capacitance times delta V, which I know is 24 volts, which is 154.3 microcoulombs. Now, what I know is, I know now that, so if I'm going back through in, the accordion that I have built, where I have this becomes C1, 2, C3, C4, then this becomes, whoops, C1, 2, C3, 4, C5, then that becomes C1, 2, 3, 4, C5. Okay, now, I know that the charge over the whole capacitor is 154 microcoulombs. That's part one. Prepare to start part two.